Hi, this video concludes our coverage of AVL trees. We're going to wrap this up with an analysis of AVL trees. We want to see that these things are actually efficient after all this. So as we've seen, the performance of all of the important operations on an AVL tree is all proportional to the height of the tree. So in order to have fast operations, we need the height to be small. The claim that we're going to prove shortly is that the height of an AVL tree is big O of log n. Remember that the minimum possible height is big O of log n. The goal is to match that best possible height, which is logarithmic. Let's recap what we have to work with. The balance factor of a node is the absolute value of the difference between the heights of the two children of that node, and the AVL balance invariant says that every node's balance factor has to be only 0 or 1. Balance factor 0 is okay, 1 is okay, 2 is too much. 2 is over the line. It's too imbalanced to count as AVL. So what we want to prove here is that every AVL tree has height big O of log of n. So if you have a binary search tree that obeys this invariant, where the balance factors are only off by 0 or 1, that implies that the height of the tree has to be at most logarithmic. So we're doing a worst case analysis here. We're asking what is the maximum possible height relative to n given that this invariant is obeyed. And we could analyze that directly. It turns out to be kind of tricky and makes for an awkward argument. So instead, we're going to look at minimizing the nodes relative to the height. So these are logically equivalent. Maximizing the height relative to nodes is the same thing as minimizing the nodes relative to height. So instead of saying for a given n, what's the maximum possible height we're going to get, instead we're going to say for a given height, what's the minimum number of nodes it takes to get that height. So define n subscript h, I'm going to call this nh, but n subscript h is the minimum possible number of nodes that an AVL tree could possibly have when that AVL tree's height is h. And we're going to analyze for what that minimum height is. So let's get into the argument here. So by definition, the root of a tree has height h. H is the height of the root node, so of course the root has height h. And the definition of height says that one of the children would have height h minus 1, because remember, the height of a parent node is one more than the height of its higher child, right? So one of the children has to have height h minus 1 for sure. And then the other child could have height h minus 1, or it could have height h minus 2. Remember, the AVL invariant says the heights could be the same, or they could differ by 1. And here we're analyzing for the worst case for the tree, which is the most imbalanced tree possible. So we're going to assume that the heights are different so that there is a balance factor of 1 here. So that means that our root has height h. There's one child of height h minus 1. There's a second child of height h minus 2. So the total number of nodes in this tree, remember nh is the minimum number of nodes in an AVL tree of height h. So in this worst case tree, nh would be nh minus 1 plus nh minus 2 plus 1, because there would be nh minus 1 trees in the left subtree here. There would be nh minus 2 nodes in the right subtree, and then there's also the root itself. We have to count that. That's the plus 1. So call this equation number 1. Now what I'm going to do is work out how many nodes are in this left subtree, the nh minus 1 side. So if we use the same equation and substitute h minus 1 in for h, so I'm just going through here and replacing every h with an h minus 1, nh minus 1 would be nh minus 2 plus nh minus 3 plus 1. Call that equation number 2. Substitute equation 2 into 1. So what I'm going to do is take this whole equation, substitute that into the nh minus 1 term of equation number 1. And what we get is nh is all this stuff. So nh is nh minus 2 plus nh minus 3 plus 1 plus the nh minus 2 plus 1 terms. And we can do a little bit of algebra to combine like terms, and we get that nh is 2 nh minus 2 plus nh minus 3 plus 2. Okay, so this is what we've got so far. nh is 2 nh minus 2 plus nh minus 3 plus 2. So that says the minimum number of nodes in a tree of height h is 2 times the minimum number of nodes in a tree of height h minus 2 plus the minimum number of nodes in a tree of height h minus 3 plus 2. Now, nh minus 3 has to be non-negative. The number of nodes in a tree is never a negative number, so that's non-negative. 2 is positive, of course. So if I just erase those two terms, subtract those two terms, I made the right-hand side of the equation smaller and did not change the left-hand side, so this becomes a strict greater than. So nh is strictly greater than 2nh minus 2. So the minimum number of nodes in a tree of height h is more than twice the number of nodes in a tree of height h minus 2. So that means that nh grows by a factor of 2 every time h increases by 2. So if the height goes up by 2, then the number of nodes has to at least double, is what that says. And so we could rewrite this in terms of exponential growth and say that nh has to be greater than 2 to the h divided by 2 power, because every time h goes up by plus 2, it doubles. So this is powers of 2. Now we can take the base 2 logarithm of both sides. So I'm just going to take the log of the left and the log of the right. You get base 2 logarithm of nh is greater than base 2 logarithm of 2 to the h over 2. And by logarithm rules on the right-hand side, we can simplify this. Remember, there's a log rule that says if you have the logarithm of a base b of b to some power, the log base 2 and the 2 to the power cancel each other out. So log base 2 of nh is greater than h divided by 2. Finally, a little bit of algebra to solve for h. We multiply both sides by 2, and we see that 2 log base 2 of nh is greater than h. So that says the height is log n. So again, this is saying that the height of a tree has to be less than 2 times the base 2 logarithm of nh. So the minimum number of trees, minimum number of nodes in a tree of height h. So even in the worst case, the height of an AVL tree is at most 2 times the base 2 logarithm of the number of nodes. So the height is at most twice the logarithm, and we would say that constant factor 2 can disappear out of the big O notation. The height h is big O of log n, which is the result we wanted. So our proof in the previous couple slides shows that the height of a tree is less than 2 times the base 2 logarithm of the number of nodes. It's actually possible to do a more precise proof and show a tighter bound that the constant factor here is more like 1.44. So about 1.5 is a more accurate representation. That's because we were sloppy in a couple places, namely this substitution here where I just deleted off these terms and ignored them. That's pretty loose. So if you do a tighter mathematical bound, you can get a more accurate 1.44 factor. But either way, it counts as big O of log n. These are different constant factors. So how does that impact the overall runtime of AVL trees? Well, let's look at the search, insert, and remove operations. The search operation goes top to bottom. It starts at the root, and in the worst case, goes all the way down to a leaf. It spends constant time per level to do that three-way decision. So there are h levels. We spend constant time on each, so it's big O of h time, and the height is log n, so that's the same thing as saying big O of log n. So that's fast. Log n is a fast runtime. Insert has the same kind of situation. To do an insert, first there's a top to bottom search, starting at the root at the top, working our way down to find where to insert the new node. So that takes big O of h, which is big O of log n time. Creating the new node at the bottom takes constant time. And then there's the bottom to top restructuring loop. We start at the bottom, work our way up, looking for an imbalanced node. If we find it, we do a tri-node restructuring, and that takes big O of h, which is big O of log n time. So there's a total of log n time to go bottom, or to go top to bottom, constant time to add the node, log n time to go bottom to top to do the restructuring. It all adds up to log n time. Erase is the same kind of situation. It's log n time. In order to erase a node, you go top to bottom to find a node to erase. That takes logarithmic time. If you search for the in-order successor, that's another big O of h time, which is logarithmic. And then removing the node is constant time, and then there's a loop that goes bottom to top looking to do restructurings. Remember, it's a loop. You might have to do multiple restructurings, but that's another big O of h time. So altogether, big O of log n time. So let's see how AVL trees compare to the alternatives we've seen for maps. So here are the map operations in this table, and I've got a column for plain binary search trees with no balancing, the association list, the vector of pairs that we introduced at the very beginning of maps, and the AVL tree. And what we see is that they all take constant time to create an empty data structure, unsurprising, but In every other operation, the binary search tree could take up to linear time if you've got a very imbalanced tree. The association list takes linear time to search all of the pairs in the vector, but AVL tree only takes logarithmic time. And log n time is way faster than linear time. So AVL tree based map handily outperforms the binary search tree or the association list. All of these operations, searching, inserting, and erasing, are only big O of log n time, which is super fast. It's close to constant time, not quite, but close. So these self-balancing trees, such as AVL trees, are a clear winner over plain binary search trees or association lists. There's really no reason to use them if you have access to an AVL tree. AVL tree is the way to go for a map.